Just great to have everybody back.
The
Hope
background.
you're re-energized. Our next speaker is Mike Mahoney from the UC Berkeley Statistics Department and International Computer Science Institute, where he is director of the NSF-funded Foundations of Data Analysis Institute. He's an expert in particular in ultra-large scale machine learning, and he's here today to talk about practical theory and neural network models. Take it away, Mike.
All right, so let me know if there's a problem hearing me, but I'll assume things are okay if I don't hear otherwise and see.
Sounds good. So far, so good.
Good. All right, thanks, Rich, for the introduction. And let me get rid of the two lights in the background. And thanks for the chance, the invitation from the organizers to have the chance to tell you about some of the things we've been working on. So what I want to tell you about is some work we've been doing, and I think you'll see a lot of themes in the last two talks and probably the talks tomorrow. And I want to scope it out in a certain way, and I'm calling it practical theory. So I'd done work in statistical mechanics, and I've done work in statistical learning theory. So I didn't come at this with a particular prior as to the technique I wanted. The prior, in a sense, is that we had done a lot of work in randomized numerical linear algebra and spectral graph theory, both theoretical work, theorem proving and that sort of thing, but also trying to apply it and trying to apply it at scale. But that, large means different things to different people. And there's oftentimes a reasonably large sort of theory practice disconnect. But if you're really careful, you can back out interesting theory from the real problems. And so when I saw this stuff in neural networks a few years ago, it seemed like a nice thing to think about for two reasons. One, it was really sort of computational math at scale in a way that machine learning didn't have prior to then, right? Prior to then, you just get a bunch of data and do 3 steps of a power method and call it good, right? And then ensembleize it. So this really stress tests computational math ideas sort of in an interesting way. And I remember when I first heard about this double descent and overparameterization, one, I thought it was interesting, but two, I thought it was interesting that so many people thought it was interesting. And the reason is basically the following, in a lot of physical systems, if you perturb the system in some way, for example, send in energy, in an ML system, send in data for the training process. If you send in energy, certain quantities change, right? The average temperature of the system might change, but there's certain points where you can just dump a lot of energy in and the temperature does not change at all. So for example, going from liquid to gas for water. And this is a fluctuational property. This is a heat capacity. So heat capacities are second logarithmic derivatives of variables that are conjugate to the dual variables depending on the ensemble you're in. And the point is, these are first-class citizens. These are not sort of corner cases. These are first-class citizens in statistical mechanics. And they really aren't in machine learning. And so if you imagine dumping data into your model and training with whatever protocol you have, the question could be how sensitive is some measured property of the model, the temperature in the example I gave you, but generalization in ML. And in some cases, it's probably not too sensitive. It changes, generalization changes gradually. And in other cases, it might change dramatically. So I think sort of a lot of you may sort of know that, and you say, oh, well, statistical mechanics shows you have these phase changes and it changes dramatically. But then you get into weeds of replica theory and lots of complicated stuff. But the qualitative idea is that, that there's a sensitivity. And this isn't, I don't think, inconsistent with a lot of ideas in statistical learning theory. It's just not the way people usually think about it. And so the interesting thing here seemed to be that people really didn't think of generalization as the sort of volume or fluctuational capacity that was a first-class citizen. And so what we thought started to think about was can we use ideas maybe from matrix theory or from statistical learning theory to operationalize some of those ideas. And so what I'm calling this is a sort of practical theory. So I think it's really fundamental theory, but it's theory sort of designed to be sort of practical in some sense. Let me start with a introductory thoughts. And I want to sort of scope this out in terms of basically a way to think about some of these things. Then maybe I'll talk about some empirical results, because one of the points of practical theory is, you should look at the data and then form the theory. And so, and not sort of come from general principles as much. And so I want to tell you basically empirical results that are the case for state-of-the-art models. And then I'll describe a theory, and I'll say what I mean by theory in the introductory thoughts. It's not a bunch of theorems, but I'll say what I mean by theory. And then I'll describe how to use the theory, because I think a practical theory is sort of one that can be used for real problems. And I realize that the way I'm describing it's probably a little unfamiliar to a lot of people in the ML audience, and so I'll describe some of the work we've done in the last few years, maybe to try and operationalize this, not operationalize it in a practical sense, but in a theoretical sense, in a way that's amenable to the way a lot of maybe people in statistical learning theory think, and some particular theorems. And so I'll describe some results we have there. All right, so let me start with some introductory thoughts. So here's a question that I don't actually know the example. So assume that you're given a state-of-the-art neural network. And de facto, currently that means computer vision, CV, or natural language processing, NLP. Maybe in 5 years, there'll be other areas, but state-of-the-art models. Can we tell if it's overparameterized or not? I mean, I know lots of sort of tricks, if you do model pruning or you do quantization, you damage the quality of the model, then you got to refine it. But if it's fairly easy to refine it, maybe you're overparameterized. Maybe there's some fat in the model, and maybe you need to get to a good model going via that fat. But but that's sort of a bunch of rules and heuristics. I mean, in the case of linear models and kernels and basically linear models, the answer to this is clear. There's n and there's p, and you're rectangular one way or another. But so essentially, this is a question to say, what is an effective notion of a load parameter? If you think of this in terms of restricted Boltzmann machines, where the load depends maybe on the quantity of data, maybe on the quantity of data relative to the size of the model, but maybe also convolved in some complicated way the sort of quality of the data. So some of the tools I'll be talking about actually, I think, are to the point where we can almost answer this question, but it's not quite clean enough, and we don't have something written up. So I want to not ask this question, except to say we're in a workshop on overparameterized model, and so can we tell if a model is overparameterized? So I don't know, actually. State-of-the-art model. I don't mean a one layer or something. And so, so I'm going to ask a slightly different motivating question that we do know the answer to. So let's say that I'm not at one of 5 companies that have gobs of training data, and I'm not training a model because I don't have lots of GPUs. And you give me a model. Can I tell whether that model is any good? Right? I mean, if machine learning is going to become an industrial pipeline, some people are going to train, some people are going to validate, some people are going to deploy. And I need to answer the question, did you give me a good model? Maybe you damaged it on purpose, maybe you damaged it inadvertently. I mean, this is the way engineering systems work more generally. So can I predict, I don't want to say generalization, because generalization has a particular technical meaning in ML, as you know, but can we predict trends in the quality of the model? Is it good or bad? Without access to, go to an extreme case, without access to any training data and testing data. If there's someone on the line from Google or Facebook and you're willing to share with me all your data, I'll reframe this question. But if you're not willing to share with me all the data that you use for training, and you're not willing to share me all the experimental protocols that are pretty hard to reproduce actually, in terms of step size and so on and so forth, and share with me all your computational resources, let's go to the other limit and say, what can we learn with little or no data? And so without any access to training and testing data, can I predict trends in the quality of state-of-the-art models? So there's a footnote here, so the spoiler is yes. But before we get to that, I mean, I think this is an odd question for a lot of people that think about machine learning. I mean, some people might say yes or no, since a theorem says such and such. Some people might say yes or no because of some Bayesian prior, or some distributional covariates, whatever. Some people might say, yeah, maybe if the convolutions are smooth, but not for NLP. Some people might just say, I don't know, I build systems, I don't even think about such things. And I, when I started thinking about this is sort of strange, right? Because this MO, this methodology is not how people build bridges. It's not how people do brain surgery or explore for oil or trade stocks, right? It's not how people design drugs. It's not how people do any of a wide range of things that are sort of built on some scientific principles. And we're asking for a theory of over-parameterized models and how it relates to under-parameterized. This is not how people build theory in other areas. And so it's why is this the case that we do it for AI or ML? So this may be a question for the panel tomorrow or more general, but I mean, just keep that in the back of your mind as I walk through some of these results. So I want to distinguish here, what is a theory and sort of what's the role of the theory? And I want to distinguish maybe 2 things that, to summarize and oversimplify sort of on one slide, between, let's call it a scientific theory and a mathematical theory, for lack of a better set of terminology. I mean, one is sort of an explanation of nature made in a way consistent with the scientific method, by which I mean I go out and measure stuff, I form a theory, it's mathematical or not, I make predictions and I'm right or wrong, and if I'm wrong, maybe, you know, my theory is incorrect, and if I'm right, I get a little bit more confidence in it. But in particular, I ask falsifiable questions. And so this is really descriptive. It's trying to describe the way the world is, and as opposed to a mathematical theory, statistical learning theory, which is sort of a bunch of theorems that provide sort of a structured collection of way to think about certain mathematical things. And oftentimes the way this is used is in a prescriptive or normative sense. You know, this is the way the world should be. So I mentioned that, and I think this is sort of an important dichotomy. And in particular, the motivation for the title here is that state-of-the-art neural networks this is just a very practical business. And so I think it demands a practical theory. So I'm going to, for the most part of what I talk about here, until I get to the end, we're trying to relate this back to the way we in machine learning think about it. I'm going to have something more like a scientific theory. So I don't want anyone to complain that I don't have any theorems, because that's not the goal till I get to the end. I want a practical theory that's going to do well on practical state-of-the-art problems until I get, 45 minutes in or whatever. And so, why does this matter? I think it guides, I mean, the questions you ask guide the type of theory you do, but also the type of theory you do guides the question you ask. So for example, I'm going to come up with a metric. It's a, call it alpha. It's a power law exponent. It doesn't matter at this point what it is. It's some metric. And so the question is, what do you do with that metric? Do you use that metric to make falsifiable predictions? Maybe on the quality of state-of-the-art models, predicting trends in the quality of state-of-the-art models without access to any training data or testing data. I mean, I could make a prediction, I could be right or wrong, and that suggests that my metric alpha is capturing something correct, and there's a counterfactual step there in terms of the scientific method. A different thing is I could use alpha and I could say, can I just use it as a regularizer? I don't know if this is the way the world is, but I want this to be the way the world, I want to impose this on the world. I want to use this as a way to train models. And we've given talks on this, and almost inevitably I get asked that question, can we use this as a regularizer? And we know the answer to that, but that's not what I want to talk about here today. But the point here is that, if you have a metric, are you going to use it to ask a counterfactual question, or are you going to use it to impose structure on the world in your models? Because if you're imposing structure on the world in your models, it's very hard to ask these more counterfactual questions. Something else that's going to pop out here is, let's call it size versus shape, right? We all know the Gaussians have a size and a shape, right? They have a mean and they have a variance. And a lot of statistical models have, call it a scale parameter, a size parameter, and a shape parameter. And matrix norm is a size parameter. It's a norm of eigenvalues. Maybe the shape of the eigenvalue distribution, call this a shape parameter, sort of meaning informally. A lot of, Peter mentioned uniform convergence, but a lot of those bounds, it's pretty hard to deal with actually with shape parameters. It's much easier to get a, deal with size parameters. And so that provides a selection bias for certain types of theoretical statements you might want to make, which then couples back to this describing versus prescribing. And what we're going to do is sort of back out size and shape parameters from state-of-the-art models. Constraints on the type of theory, worst case bounds work better with norms. Statistical mechanics, oftentimes it's described as average case. That's just not correct, actually. It's more like typical case. There's a statement about I'm averaging over something, but there's a statement about there's almost nothing that's different than the average. And so that's a much stronger statement. If you know about quenched versus annealing, it's related to that. And so shape is more related to volumes, right? So think of Moore-Penrose inverse, right? In one regime, the underparameterized, the overdetermined, I have a minimum norm solution, and if I tweak things around that, there's not so many, depending on the Lipschitz curvature or the condition number. In the other regime, Moore-Penrose gives me a unique solution, and if I go just a little bit different than that, boom, things blow up, and I get a huge range of possible solutions. So when you have a singular perturbation like this, zero isn't approximately the same as approximately zero. And I mentioned this last thing about determining causes from data, because everyone sort of says, well, yeah, we can't determine causes from data, but I think people really want to. And I'll have sort of a cautionary tale about how we use this in the context of a contest last year to try and back out, some understanding of what's actually going on, which doesn't involve constructing a new metric, but basically involves looking for Simpson's paradoxes and then using domain insight to back out some falsifiable predictions. So this is sort of just general background maybe on how I was sort of on the scope. So now I want to describe some empirical results. And I could talk sort of for 2 hours about this. So I'll talk just a little bit, and I'm going to summarize sort of a large and complicated story just in relatively small number of slides. But these are empirical results for state-of-the-art models. So I'm not training on one layer or something. I mean, this is state-of-the-art models. So if we're going to talk about working with state-of-the-art models, don't evaluate your method on 1 or 2 or 3. Evaluate it on, when we started this, there was dozens. And we're using publicly available models, partly because of the way I scope the question. Can I predict trends in the quality of generalization without access to any training data or testing data? You put a model out there, I go pull it down, I chew on the model. I don't have any data, and so if there was data made available, I'm not going to use it. Dozens. 2 years ago, there was hundreds, now there's thousands. The vast majority are computer vision and natural language processing. You got to be very careful if you use bad or toy models here. And in particular, if you have models with a very wide range of qualities or very wide range of structures. And if you do use that, it's far from obvious that the principles that would work on toy models would work for state of the art. And you may get qualitatively different sort of predictions depending on how you segment the data, and we'll see that. And as a design goal for what I'm talking about today, we're not going to train any models. We've done a lot of model training and so on, but I want to work with pre-trained models. Training is a hard business. There's a lot of weed level details to sort of argue about, and I think it just confuses what I'm trying to talk about today. So I mean, I'm happy to talk about this separately, but we'll work with pre-trained models. All right, so we spent a while looking at these things, and long story short, a very, very fruitful way to look at a wide range of state-of-the-art models is via its eigenvalues. And I say this not as a person who likes eigenvalues. I say this as a person who just looked at a lot of things, and it turned out to be a very fruitful way to think about these things. Now you got to be a little bit careful. So I'm going to show you a bunch of plots, and a lot of the plots are going to be the eigenvalues of X, where X is W transpose W. So say I have a weight matrix at some layer W. I'm going to look at its singular values. It's the eigenvalues of W transpose W. And the idea might be that, we want to capture something about the correlations that the model is capturing in the data. Now, importantly, I'm not positing a statistical model, bulk plus spike, or what NTK, where you're random like, and the spectral norm doesn't change or anything like that. I'm going out and looking at a model that you or someone else put out in the world, and I'm chewing on that model. So I'm going to look at its layers. So there's a lot of questions. What about convolutional layers? What about this, the size, the matrices? So the long story short is, if you look at models before whenever, 2013 or 2012, they looked like the following. Linnet 5 on MNIST, for instance. If you look at the distribution of eigenvalues, it looks something like this. These are the same plots. One is zoomed in. And what I see is a histogram of eigenvalues. They have some shape. The red here is the best MP fit, the best fit to a Marchenko-Pasteur distribution. This is the rectangular version of Wigner's semicircle law, and the best fit to a Marchenko-Pasteur distribution. And it's pretty good, actually. I mean, it's very well described here. You get a strong cutoff here, and then you have a bunch of stuff. And if you don't zoom in, but you zoom out, you have a dozen. And so this matrix is, I don't remember what it was, 500 by 1,000 or something. And you have on the order of a dozen eigenvalues that are well outside this Marchenko-Pasteur regime. So I don't know whether this eigenvalue right here is, that's sort of at the BPP transition, if you know what that is. That's right at the edge, so maybe that's a signal, maybe it's not. So, but you get a sharp edge here, and you get a whole bunch of eigenvalues out there. So older, smaller models, less well-trained models, as it turns out, really look like what statisticians call bulk plus spike. So statisticians will say, I'm going to posit a model that has 10 eigenvalues that are large, maybe 1, maybe 10. And the randomness gives you a Marchenko-Pasteur bulk. And the question is, can I find these eigenvalues that stick out? So we're doing something a little bit different. We're looking at state-of-the-art models. This was state-of-the-art 20 years ago, not now. And we're saying, what are its properties? And the long story short is, those things look like bulk plus spike. These spikes contain the signal, et cetera, just like you'd expect. Essentially, every state-of-the-art model post-2013 does not look like that. It looks like this. This is AlexNet, but it's a very typical result. What you see here, again, the red is the best MP fit, and this distribution on the right and on the left is very, very non-random. So I'm showing you on a linear scale. I could show you on different scales that hides and and makes clear sort of different things. So there's no perfect way to view this, but the fact that there's a lot of mass here, this is very, very significantly not random. You do not get a sharp transition at the edge, and you have mass bleeding out very far. And so essentially, state-of-the-art models post-2013 have a heavy-tailed structure in their weight, in their weight matrix correlations, not in the weight matrix elements generally, but in the correlations of the weight matrices. So the weight matrices typically have a scale because you clip things during training, but the correlations in the weight matrices. So I go and I look after the fact, what did you learn? And the answer is essentially, I learned an ellipsoid with a long axis over the, with a heavy tail over the long axis. So these are not random matrices. These are very, very non-random matrices. You know, these are state-of-the-art models that do state-of-the-art on NLP and computer vision tests. So they're not random. But if you look at the eigenvalues, they have a heavy tail structure. So there's a question before about, you know, sometimes in neural spike trains you see this. Yes, you see this in neural spike trains. It's sort of, coincidental that it happens to be in neuroscience, and these are neural networks. That's not the issue. You know, the point is that the neural spike trains have, you know, they're strongly correlated systems, and the way one set of spikes might behave is strongly correlated with another. They're not bulk plus spike, and they're not random. They're strongly correlated systems. You see a similar thing in finance. You see analogous heavy tail structure in financial time series, these long range correlations. And so you're seeing exactly the same thing here. So this is a typical result. I could show you, you know, hundreds of others. You get a lot of funny stuff. Sometimes you see a dip here, but you still see a large, you know, heavy tail mass sort of spreading out. And I could show you many, many others. This particular slide is a little bit stale. What I want to show you here is alpha is, if you look at ImageNet and Allen NLP, this was, you know, 3 years ago, when these were the first ones that were out. And I look at, there's many layers. I fit a parallel exponent, the heavy tail exponent. The particular functional form doesn't matter. It's actually a truncated parallel. To the eigenvalue distribution, and ask, what is the power law parameter? And you might hope it's 2 or 3, partly for the reason Peter said, that you have a very narrow band of regions if the spectrum is decaying slowly, where you might get the cancellation he wants. That's probably what's going on under here. And then you see a lot of eigenvalues that are a bit larger, meaning that these layers are maybe undertrained or not quite as well. You know, correlations aren't captured quite as well. So you see this here. You know, if we're saying that the heavy tail here on the eigenvalues is capturing something about correlations and weight matrices, that might mean that if I release a model and a year later I release another model, and the second model is better trained, I might expect that the eigenvalues pull down, so the parallel exponents and the eigenvalues pull down a little bit, that the correlations are more strongly captured, and you see that. So, you know, here's a histogram of eigenvalues in GPT versus GPT-2, and it improves over time. So this is actually a prediction we had about three years ago, and you see that. And so, you know, this is a sort of prediction that you could make to say, if I train GPT-2 to a factor of 10 more data, I would expect certain things. It's not quite as simple as this. We now have a more refined understanding, but, you know, you might expect that the correlations are better captured, and the short answer is yes. The long answer is a bit more involved. But the point here is that in natural language and computer vision and a lot of things, you really have these heavy-tailed ESDs. So the short answer is that old models, small models, whatever, look like bulk plus spike. Their eigenvalue distribution empirically looks that way. Why? We'll talk about why. But everything post-2013 in computer vision, natural language processing, has a heavy tail structure over the eigenvalues. And there's lots of details in fitting heavy tail models, but it has a heavy tail structure over the eigenvalues. And these are very non-random systems. And so the idea might be that the training process itself, because of all the knobs or whatever is going on, captures correlations over many size scales. So we want to try and formalize that. But these are the empirical results that we'll be working with. So we saw that, and then we sort of said, geez, I want to develop a theory, in the sense that I used the word before, predictive theory, that might answer a question such as, can I determine whether I'm overtrained? Can I determine whether I need more data? Can I make predictions in the quality of state-of-the-art models? And so here's the 101 and the 102 and the 103 in random matrix theory that sort of underlies the theory we have. So Wigner semicircle is sort of drawn pictorially here. There's interesting stuff going on at the transitions if you don't know what this is, because you get an asymmetry in the tail structure. This is the Tracy-Whittem window. We're well outside that. And so we want to distinguish, you know, being random in this Wigner sense versus being very not random. weight matrices are usually not square. There's a range of other practical issues. You need 102 random matrix theory, which boils down to similar ideas. Marchenko-Pasteur, this is the functional form of it. If you look at the ESD of the weight matrices, in a random matrix here, it'll correlate, it'll converge to a Marchenko-Pasteur distribution. The exact shape of it depends on the aspect ratio and the variance structure. So there's two relevant things. One is we're looking at global bulk statistics about the overall shape, and then the local edge statistics, the details of the tail. Sorry, so the details of the transition from the bulk to the tail and whether or not there even is. You can use heavy-tailed random matrix theory, and this is a slide I don't want to go into the details of, but if you fail to have the moments you want and you're not in the Gaussian universality class, is the situation hopeless? And I ask that because the empirical fact, as I just said, is that everything post-2013 has this sort of heavy-tailed structure. So if you're modeling it with random matrices in the Gaussian universality class, you can get some insights, but it's going to be limited at some point because the data just don't look that way. And so, how do you bridge those two? And so depending on the details of the model, and this is the sort of thing that I think uniform convergence theory does not handle particularly well. Some of the statistical mechanics ideas do handle a little bit better, but it's a hard regime to deal with. And you have a couple different universality classes in this heavy-tailed regime for random matrices. Now, of course, we're going to be using random matrices here not to model noise, but to model signal, strongly correlated signal. So that's a caveat. But and roughly the taxonomy of universality classes here is the exponent. This is the hypothesized exponent, not the empirical. But is the exponent less than? Is it greater than 4, or is it between 2 and 4, or is it less than 2? I'm getting a little bit of noise here, and I want to make sure that my my wireless didn't go down. So can someone say a thumbs up and make sure that I'm still connected and they can hear me?
Yeah, we can hear you. Thanks.
All right, so I'll just ignore what's going on here, I guess. So I think there's a lot of it. So the work we use actually used ideas from Bouchard and Potters, who are physicists working on distorted systems. They worked in finance. Neuroscientists use similar techniques. This is back in the 90s when the theory was parameterized in the way physicists like. In the last 20 years, there's been a lot of work, sort of call it mathematizing these results, coming up with sort of more theorems. And so I think there's a lot of interesting questions here. And in the last few slides, when I talk about putting this more in the language of ML theory, I'll talk about some of those. So I think this is a great slide, and there's a lot of open questions for anyone who likes these sort of technical things on this slide, but let me not go into the details there. The point is that we're going to really be working with heavy-tailed random matrices, and it's because we're modeling strong correlations over many size scales, essentially. So based on that, we came up with a theory. This is a phenomenological theory. It's not a bunch of theorems on what we're going to call 5+1 phases of training. So there's a degenerate case where you lose rank. If things really are random, you never lose rank, is the short story. I mean, if you're perfectly square, and there's a few corner cases, but otherwise you don't lose rank. So if you've lost rank to machine precision, single-digit machine precision, 10 to the minus 6, something's usually broken in the model. But roughly, think of it as you can be a Gaussian universality class. We're calling it random-like. Not that you're random, there might be signal there, but looking through the lens of global random matrix theory, you can't see the signal. And so it looks random-like. You can be basically bulk plus spike. So there's a bulk here, there's a spike. Or you can be really heavy-tailed. And so you're well out. So bulk plus spike is Gaussian universality class with some perturbations. Heavy-tailed is non-perturbatively different. It's a different universality class altogether. And you can have a transition between the different regimes. And you can imagine these transitions as it gets a little bit complicated in practice. But think of this as 3 regimes, 2 transitions and a corner. And if this looks bizarre and you're saying, why would you do this? I mean, there are theorems out there that say in some idealized limit, if you're infinitely rectangular and you're a 2-layer or something or other, then I get good generalization, and my eigenvalue distribution, my spectral norm, which is my worst case measure over my eigenvalue distribution, my spectral norm does not change at all. That's a perfectly legitimate theorem. And it is appropriate for systems that are in the random-like phase. So the NTK limit, is basically a variant or first cousin of something like this. If you ask for a perturbative variant of that, you may be in the bulk plus spike phase. And this is appropriate if you're working with Linnet 5 and something like that on MNIST. And so, a very different thing is if your empirical matrices are heavy-tailed, you want to try and capture that. So so the 5+1 phases, and from that perspective, smaller, older models really are bulk plus spike. And the way you should think about this is there's a scale to the system. There's a scale given by roughly Tikhonov regularization. And by that, I don't mean to draw the distinction between that and lasso or SVM with ridge. I mean, basically it's F plus lambda G. There's an F, there's a G, and there's a lambda that modulates the scale. And if you're above lambda, then you're signaling. If you're below lambda, you're noise. So bulk plus spike is that. We have in a lot of these post-2013 models what we'll call a heavy-tailed self-regularization. I'll say what I mean by that in a few slides. The weight matrix strongly correlated and highly non-random. We're going to model the strong correlations with heavy-tailed random matrices. And we're going to, so we're modeling the signal by these heavy-tailed random matrices. Then random matrix theory, I mean, Marchenko, Pasteur, ESTs, maybe I should remove the MP there, will also have heavy tails. So the eigenvalues are heavy tails, not the weights. And essentially the TLDR is that everything looks like this, and there's a much more complicated structure if you wanted to go into more detail. So as for mechanisms, there's multiple mechanisms that can give rise here. Physicists have this term called self-organized criticality. You could have multiplicative updates in the weights or in the weights in Fourier space. For using the method, we don't need to posit a mechanism. I mean, clearly there's an interesting question as to what that mechanism is. I mean, so, but I mean, think of an operational theory like quantum mechanics. You don't need to know the mechanism for everything to use the theory. So for what I'll talk about here, we don't need to know that mechanism, but clearly that's of interest, and I'll have a little bit more to say about that. And how does this relate to regularization? Because I'm calling this self-regularization. And I think the thing here, the best way to think about this is that, you know, everything is regularization. I mean, you know, the abstraction of coming up with an approximation algorithm, and you have noise in the stochastic algorithm with SGD, you compose it with some other layer, you feed it to a downstream classification test as noise. I mean, this first reference here, I think, has 50 things that are regularization. And so, you know, that as a primitive notion really gets emasculated a little bit in terms of thinking about it if everything is regularization. So think of it as maybe explicit regularization. You replace min of F with min of F plus lambda G, just the usual thing. There's this notion of implicit regularization. We had something about 10 years ago where we sort of characterize this very clearly, you know, where basically the idea of approximate computation, I approximate min of F, so I get an approximation algorithm to that. It exactly optimizes implicitly F plus lambda G. And in the last few years, this has gotten more attention here in the context of stochastic gradient algorithms, but the same idea holds more generally as we described there. So the heavy-tailed self-regularization here is regularization, and it's regularization in the training process. And the one way to think about it is it's regularization essentially because the training process depends so heavily on the data, right? This isn't least squares where you define a few features and then call, you know, a black box. I mean, the training process depends so heavily on the data. And you know, the idea here I said is we're squeezing out correlations from the data in many size scales. So a prediction of the theory will be that if you train to pure noise or something, you should get very different results. Maybe you shouldn't see this. And so in fact, we do see that. So think of this as it's heavy tailed because they get correlations over many size scales, analogously to the finance or the neuroscience thing. But this is because I'm training to good data. I'm training to reasonable quality data, not random or bad or arbitrary or whatever. And I put this slide in this morning because someone was asking something. I mean, the way to think about this, I think, is we're trying to use the statistical mechanics idea and bridge it to the way statistical learning theory uses techniques. But the statistical mechanics isn't of the form write down an Ising model and prove a theorem. It's more like phenomenological statistical mechanics. So I said that the MO in machine learning is very different than the way you'd build bridges or build vaccines. I mean, as you know, there's been a lot of interest in the last year in developing vaccines, right? How are those things developed from the perspective of what we're talking about today? And it's developed in a lot of ways, but one piece of it is if you're doing computational work on that, right? And so there you will measure an active site and you'll change something in a computational protein and you'll measure stuff. And so you're using statistical mechanics. And so you have a theory, a surrogate theory built on top of the underlying theory with parameters that you fit to the data. So you're not proving a theorem, but you're really using the theory. And it's known there, for example, people think about like proteins and protein structure. So here's a story. We'll get back to theorems and we'll get back to derivations and stuff in a slide. But, you know, as like a random matrix, right? How could it not be? And a protein If you think of it as a random matrix, it might have a very noisy non-convex loss surface. But empirical fact, if you take a natural protein and you heat it up and cool it down, heat it up, cool it down, heat it up and cool it down, you essentially always converge to the same configuration. Just, you do it 1,000 times, you'll always get the same configuration. There's a few exceptions that prove that rule, basically. If you take a natural heteropolymer, but it's a random sequence of amino acids, that is false. Heat it up, cool it down, you get a blob that's meaningless. Heat it up, cool it down, you get a blob that's meaningless. You do this 1,000, you do this the age of the universe. You never get the same thing twice. And so in the one case, you really have a rugged landscape that has no large scale structure, and you just get lost in local minima. In the other case, essentially you have a rugged funnel. And so with respect to the least squares and the more Penrose inverse and the singular perturbation, you should think of this as like maybe the underparameterized regime where, you have a solution, and if you perturb things a little bit, you're still pretty near the solution, the volume doesn't blow up. Whereas in the other regime, the more Penrose gives you the minimum norm solution, but because the perturbation associated with more Penrose is singular, if you're not exactly zero, but approximately zero, the volume blows up and you have very weak control in anything. So I think that's a good analogy, except here, it's this structure, this parameter along this x-axis here is not n over p or something. It's something about the load, the quality or quantity of the data. So we don't have that formalized, but I think that's the way to think about what we're doing. And so really we have a rugged well, and so we're engineering a rugged well. So the training process engineers a rugged well, and the heavy tail structure in the weight matrices captures this well at sort of the large size scale. If you don't believe me, pip install Weight Watcher. I mean, we have a nice, we're watching weight matrices, so we figured we should have a software. So pip install Weight Watcher, it does this and a range of other things, and try and break it. So it does everything I've been talking about, and the stuff I'm talking about, it's all online and reproducible. So try and break it and get back to me. All right, so I want to talk about using the theory, and then maybe expressing this in sort of language that maybe a little bit more familiar. So let's use the theory. So you could use theory in different ways. One, you could use it for model diagnostics and validation and developing hypotheses, make predictions about transferability or generalization. You might do post-training modifications. I get a model and I want to tweak it a little bit. It's not really good theory. That's not empirical risk minimization. When does a model perform well? A very practical question is, that doesn't arise in NIPS papers, but will buying more data help? I need to spend X dollars on data, on machines, on people. Where should I allocate those resources? Will training longer help? Will quantizing or distilling help? And can I answer these questions without spending $1 million in GPU resources? Without which involves a lot of peeking at data and so on. And of course, you can construct a regularizer to do better training. So I'm not going to talk about that, but you could do that also. So one thing we've seen, we talked about, and in this slide, I'm just going to put up just to mention. So this slide, in the talks I've given in the last few years, I've got more intrigue and more upset for this slide. And so I just want to sort of mention this and pique people's interest. I mean, one question, if we're having a theory, is we predicted 5 + 1 phases, can we exhibit them all? And it's hard to answer that question if I'm going to allow myself to fiddle with lots and lots of hyperparameters. So the short answer is, can I exhibit all 5 phases by changing one parameter, say just the batch size? And the answer is yes. And just the learning rate, and the answer is yes, or something. And so I think this suggests an a posteriori diagnostic to ask whether a model's been trained, and if training a factor of 10x longer will help, and so on. But let me just leave that aside to say that you can use this to the phases I'm talking about do exist, and you can exhibit them all by changing one parameter. So let's say I want to predict test accuracies. So there's just lots and lots of metrics out there, and if I'm going to go measure models, one thing I might find is norms, log norms in particular, because you're taking an average over layers, and the average log norm is the product norm in log units. So let's say I look at norms, spectral, Frobenius, a lot of different things. I'm fitting different weight matrices, so I'm measuring not just the size of a matrix, but the shape of it, the power law shape of it with alphas. I might take the average alpha. I might combine the two. We had a paper a couple of years ago that had sort of a physicsy style argument to suggest why, for small values of alpha, we should combine them in a certain way, and we did. And so, long story short, they perform, all the metrics actually performed reasonably well if you're working with reasonable data. Subsequent to that, we went and said, essentially, in biomedicine, which this doesn't happen much in machine learning, but in biomedicine, people do meta-analyses. They go back and look at hundreds of studies, and they do a meta-analysis of them. So we did essentially the first large-scale meta-analysis of hundreds of state-of-the-art models. And this is a dense slide just to say you can look at norm-based metrics. They do well in a bunch of cases. You can look at metrics having to do with the shape, these power law fits. They do well. And so I could talk about this in some more slides about how they do well. But I mean, trust me, I mean, you can predict state of the, trends in model quality for state-of-the-art models. The quantitative stuff matters. So the details will matter. And so, for example, some summary statistics on VGG versus ResNet versus DenseNet, or summary statistics on a range of NLP models. So let me not go into these slides, but instead to show you some pictures that basically underlie these numbers. So, you can use a theory like this to say, I want to do diagnostics on a 50-layer thing. So I could look at VGG with some number of layers. I could look at ResNet with some number of layers, or DenseNet. And I think a lot of people have a sense that, more stuff is better, more layers are better, right? And so ResNet has a very particular structure above and beyond VGG. What I have here is x-axis is, the layer number, y-axis is alpha, the shape parameter. And you might conjecture that if small alphas are good, then small alphas between multiple layers are even better. And what you see is that that is true for ResNet. That's not true for VGG. And so, the hypothesis would be that the reason this works is because it's enabling some sort of information transfer across the layers. I think people will say, yeah, that makes sense. People, I think, have a sense that more is better, and so adding more layers like DenseNet can only help, because the neural network just won't find things if it doesn't want it. And these empirical results just suggest that's empirically false, right? You look at DenseNet and you do not get this, small value of alpha as you march down the model. The model chokes and it can't figure out where to send the information. And so if you're designing architectures, beyond state-of-the-art CV and NLP to new areas, you could use this maybe as a diagnostic to help you how to do that. Analyzing pre-trained models. You can look at, I mentioned before that do I have it on the next slide? I do have it on the next slide. Let me skip this one and go to the next slide, because let me go through this. So you can look at the in BERT prime, BERT double prime, GPT, GPT-2, the GPT-2 series, and you could say, at a fine grain level, how does the structure of the model change with respect to the data? And to first approximation, you see that more recent models tend to be better. Heavy tail parameters tend to get smaller. You can also get a lot more fine-grained structure. For example, different layers may get short-circuited in a certain way. So here's your alpha as a function of depth, and you have red and blue. And here you have blue. There's two different types of things. This sort of suggests there's an impedance mismatch, and I think that's probably the case, but maybe don't have time to go into that here. And what you see here is as you go in the model, as you probe the model more deeply, depending on if you have a more recent, less recent model, the model has enough data to push information all the way down or not. These are things that are very hard to tell from just looking at training and testing curves. This is a much sort of more fine-grained information. One of the things that would be nice here is to say, can I tell if, not just look for positive results, but can I tell if a model's broken in some sense? And so Intel has a publicly available distillation package, and so you can go look at it, and you can ask, how do power law norms change, and how do the alpha parameters change? And they retrained a model with their distillation package. And essentially, if you look at it through the lens of the shape parameter, the heavy tail parameter, the retraining process broke the model. I mean, it was good enough for the engineers for what they were doing, but they did some damage to the model. And so now if I'm taking the original model or the distilled model, I'm actually, even if the training and testing curves are very similar, I'm actually getting two very different models, and one's plausibly much more broken, right? Okay, so how might we now want to use these sort of techniques, given that we can diagnose what we think are possible failure modes in a model? So there's a range of ways you might want to, and we've looked at a number of these. And so just to give you a sense of some of these things, these are things we've noticed based on looking at a large number of models. And the question is, how can we use these ideas, either in after-the-fact diagnostics of pre-trained models, or maybe even during the training process? So one is something that I'm going to call correlation flow. This basically has to do with the idea that if we're capturing correlations over many size scales, then good models enable those correlations to sort of flow through the model. And so this could be characterized by maybe the shape of the ESD of adjacent layers as you march through the model. And the hypothesis then would be that well-trained models have small values of the heavy tail parameter, similar at many adjacent layers, sort of, so you don't have an impedance mismatch. That's a hypothesis. Test it, and we have some evidence to support that. Scale collapse. There's a number of examples where we've seen that the size of the ESD, now not a shape, but the size, maybe the largest eigenvalue of spectral norm, of one or more layers can change dramatically, while the size of the other layers changes very little. And again, what does this mean? You have to go do some model diagnostics and analyze, but it looks like in a lot of cases that corresponds to some sort of breakage of the model. The model becomes more brittle, and so you have a hard time feeding information through that smaller size scale. And another is what we're going to call correlation trap. The idea here might be that you have particular pockets of correlation as measured by the ESD corresponding to large eigenvalues that may not be, quote, real in terms of capturing signal in the data. And sort of an example of this might be a single large element. If you have a single large entry, that would manifest itself potentially in the ESD, but not be having to do with different layers, or different columns of the matrix being correlated. And so call it spuriously large eigenvalues. We have examples of that actually in a recent paper that's actually going to appear in the upcoming NeurIPS meeting. Zhenyu Liao has a result where he's looking at Hessians, and he sees that applying random matrix techniques and deterministic equivalent techniques to Hessians, you can see even if there's no signal in the data, just as a function of the objective function in a class of generalized linear models, you can get spuriously large eigen values. And this is just due to the form of the objective. So you can imagine as you fiddle with lots of parameters, you might do something like that. So we don't yet have the corresponding result for weights, but open question, can we do this? So we're now able to poke and probe at the models in a range of ways that we couldn't before, and we can measure all these things with Weight Watcher and pip install Weight Watcher. So can you. So you don't need to believe me. You can go test this and see if the predictions we're making are right or wrong. There's a number of subtleties in particular with respect to the power law fitting, but pip install and try and break it and see what you can do. All right, so we had these results a while ago, and about a year ago, there was a paper with a fantastic title talking about generalization metrics. And then there was a related contest. And we were intrigued because they were doing something that seemed sort of superficially similar to what we had done a year before. And the contest was nominally to predict causes of generalization, maybe predict generalization and causes, but they really wanted to extract causality. So they invented various causality metrics. And we looked at this because we were interested, because we had done analysis on weight matrices, and a few comments about contests. So in contests, you sum over everything. And so if there's fine scale structure in the data, you typically ignore it. And you just sum over everything and optimize some objective. It's mean squared error or whatever. Good way to win contests is to do ensembleization, and featureization, even if you sort of the finer grains in understanding what's going on is lost. And so that's a good way to win, and we weren't doing that. It's very hard to present information leakage, right? If you change features one way, you query the contest one day, change features a different way, query the contest the next day. It's very hard to prevent information leakage. And so we didn't want to even go there, because that's not going to understand causes of generalization, right? If you get this information leakage. Good way to win contests is to augment data. Generate features by augmenting one way one day, query the contest, change features in a different way. We didn't want to augment data. I mean, those are all legitimate things to do, but they don't tell you about generalization, and certainly don't tell you about causes of generalization. Something else we noticed is that the contest said, we trained models to 0 error, and that was just false. We looked at it, and they were close to 0 error, but there was a big difference between close to 0 and 0, right? If you have 0.1% error on 100,000 data points, you have 100 data points that are not perfectly classified. Say if you're doing classification, if it's entropy, it's a little different, and you can get a lot of information for those 100 data points. So there's a big difference between 0 and approximately 0. So bottom line is we didn't compete in it, and I think there's structural problems, as we'll talk about, using our tools that we could identify with the sort of form of the contest, which I think is probably actually typical of a lot of machine learning contests, but in particular this one. But from our perspective, this was a great thing because the organizers released data, and the data were a range of qualities and various hyperparameters and model sizes. And so from our perspective, it was good to stress test the theory we had. So we did that. So roughly what was going on is there was two classes of tasks, and they correspond to different models, VGG-like and network. I'm not going to go into the details of that, but you can take the models and tasks that were made publicly available by the contest and segment them roughly by architectural parameters. Think of this as depth or width or something, sort of the coarse parameters of the architecture, and also solver parameters. Think step sizes and dropout and weight decay. These sort of details about the solver, and these are going to be two different things: sort of coarse architectural parameters and solver parameters. And we looked at a wide range of metrics. Now, we didn't look at a lot of metrics that required data, because then you might be cheating and doing this ensemble when you're doing this ensembleization and querying the model. We just wanted to take the models as given and analyze them. So we looked at a wide range of metrics. The best ones by far were so we have alpha, we have quality of alpha fit. So sometimes, because fitting the alpha is actually sort of finicky, fitting the quality of the fit was more useful. How good a fit is it? And that's correlated rather strongly with what we were looking at. Log spectral, log Frobenius norm, alpha hat that combines both alpha and the log norms. A couple other metrics here. And the point I want to make about these metrics is this is not the way people usually taxonomize metrics, but very important, I think, and undervalued here is what information do you need in order to evaluate different metrics? So we've made a big deal about not using any data, just looking at the model. But here I have three columns. One says, do you need access to the data? And the first many metrics, the answer is no. And the second one, the last few, the answer is yes. Do you need access to the initial weights? If you've done the training and you have the initial weights, then you can use them. But in a lot of cases, you wouldn't have that. And the last column is, do you basically de facto need access to GPUs? Are you doing backprop or something? And so that's, I think, a useful way to taxonomize metrics and comparing metrics that have different answers to those questions. If you're using weights and I'm not, the initial weights and I'm not, if you have access to data, I'm not, we're really comparing apples and oranges. And that's something that a lot of people in the ML community train a lot, but if you haven't trained, you don't have access to the initial weights and things. So unless you have the whole pipeline in front of you, a useful way to taxonomize and compare apples to apples when you're evaluating these metrics is to specify, do you need access to the data? Do you need the initial weight matrices? Do you have access to GPUs, and so on? So shape versus size. So size is, think of this as norms. In the way that a statistical model has shape parameter and size parameters, think of size as the norm, the largest eigenvalue. Shape might have to do with the shape of the eigenvalue distribution. And these are just different. And so what you see here is for task 1 and task 2, shape versus size segmented by different architectural, depths. And what you see is that, for example, look on the right. In some cases, shape and size anti-correlate. In some cases, they're largely independent and you have a wide range of shapes. And in some cases, they're largely independent, you have a wide range of sizes. So what the contest provided us was a wide range of model qualities with shape and size correlated, anti-correlated, were independent. And so there's a lot of heterogeneity across tasks and subtasks, and that's going to be the relevant thing. Because we were developing a theory to state of the art, and I don't know whether our theory applies on the low quality models. It does well on state of the art models, and what we have here is a place to test heterogeneity across tasks and subtasks. A lot of details in extracting shape parameters and getting the fits done right. And I'm not going to have time to go into this, but don't pull Weight Watcher and just press the big green button and say, what is alpha? You use the functionality there to look at the ESDs, and you can get plots exactly like this. And if you look at the ESDs, what you'll see is that depending on how the top part of the spectrum talks to the bottom part of the spectrum, you can get very different results. And so as opposed to work that was done in quantitative finance and in other areas where people fit these sort of parameters, sometimes you fit a power law, you fit a truncated power, and you fit the top part of the the truncation, and you fit the slope. What we do here is not that. What we do here is nail down the largest scale to be the largest eigenvalue, and we let the bottom part float because we want to capture the top part of the spectrum, and we see the quality of the power law fit as a function of the smaller eigenvalue. So in the right column here, with the y-axis is sort of the quality of the fit, and then we take the best quality fit and choose that to be x min, the smallest eigenvalue. And what you see is you can have a nice plot that goes down and up. You can have a plot that goes down and up and it's choppy, it's very flat. And if you go back and look at the eigenvalues, you can see that the top part of the spectrum, in particular in the first column, you can have it go down very gradually. You can have it go down sort of gradually and chop off too quickly, or have it go down gradually and behave differently. And so the question really, when you're determining this X min, is where, over what range of scales, what range of eigenvalues is the fit a good fit? So we have a lot of, the first row is a particularly good one. The later rows illustrate various problems you might have. And so open question, there's more work to be done actually getting better power law fits and heavy tail fits for other distributions. All right, training versus testing. Training and testing error, what we saw in the context, are often anti-correlated. You'd think better training error corresponds to better testing error. That's just not the case. I mean, oftentimes they're anti-correlated. So, but there was a lot of heterogeneity across tests and subtests. So this is actually one of the first things we checked, and this was a problem, right? When we saw that in a lot of cases, training and testing were anti-correlated, that was a concern for us, because it suggests that the models in the contest really are either overtrained or undertrained, but just not well trained. And so that was a concern. And long story short, when we observed and is a Simpson's paradox. And if you don't know what a Simpson's paradox is, I mean, this is one of these great things you should just know about, to go home and look it up. And what it roughly says is, if I have a large number of students and I have some factor, age or whatever, does increasing that correspond to better test scores or better whatever? And it may be the case that when you take all the students together, increasing this variable is positively correlated with an outcome you want. But then if you segment the students in some way, say by department or whatever, it could be that they're anti-correlated or the effect is neutral. And so clearly this is a problem if you want to back out causality. And so this is sort of, we're not trying to back out causality. In a sense, we're looking for a Simpson's paradox to say that the data have problems, so you can't back out causality, and then look at them in a bit more granularity. So what we see here roughly is that the log spectral norm, we get a difference between task 1 and task 2. It's larger within and between subgroups, but it gets larger within and smaller between subgroups. So roughly, when you aggregate the data all together, in the latter case, what you see is that the log spectral norm behaves as sort of statistical learning theory might suggest, but for every subgroup, it behaves the opposite of what you'd expect. That's a little strange. And exactly the opposite holds for alpha. Alpha, what you see is task 1, it's smaller within and between subgroups. For task 2, it's smaller within subgroups, but larger between subgroups. So it behaves sort of the opposite way you might expect if you just totally aggregate the data. But if you look at the different subgroups, it behaves exactly as theory would suggest. So this is really suggesting that there's a huge range of model qualities here. And I think, one, there's a design of this particular contest. Okay, so leave that issue aside. Two, there's sort of the general question of contests. Contests have done a lot to drive machine learning forward. But when you just aggregate all the data points and sum over some metric, what you're really doing is ignoring a lot of this fine scale structure. And so alpha really is on the nose if you look at the fine scale structure. But if you aggregate high quality models and low quality models, it does worse, precisely because it was designed to, no one wants a theory for low quality models. So we didn't do that. We designed a theory for high quality models. And so within each model group, the heavy tail metrics behaves as you'd expect, but not across model groups necessarily. So lessons learned. Don't invent causal metrics. Don't look for one size fits all metric. We identified Simpson's paradox. Then we went back and looked at domain knowledge. We looked at what we knew about high and low quality models. We looked at some of the details that I didn't get into, basically to try and identify causes, if you want, of good performance. And separating out, the leading order bit is separate out sort of model architecture knobs, maybe depth here, but depth, width, whatever, from solver parameter, hyperparameter knobs, batch size and step size and so on. And the way you should adjust one versus the other might be very different. And that's something that's really hidden, I think, in a lot of what machine learning sort of approaches do, but comes out very prominently in the approach we're adopting here. Size versus shape metrics more generally. Can you come up with a data-dependent version of them? Something we call the SVD smoothing. It requires low-rank approximations, but no GPUs, so it's sort of trivial to do. You can clip large entries and large entries based on the entries based on the gradients if you have access to data. So we have in the write-up data-dependent size and shape parameters. And the results sort of are very suggestive. I think there's a lot more work to be done here, but the initial results are sort of demonstrate that you get sort of things behaving qualitatively the right way. And that's definitely not the case for a lot of metrics, fantastic metrics that machine learning has been looking at in recent years. And I think part of that's just, we were able to use the metrics we have to go and look at a contest, identify wide ranges of model qualities, and just identify problems with the setup and segment it in an appropriate way. So lots of lessons learned. What more can we do? A lot of future directions, I think, that really demand a practical theory, and that these approaches could be applied to, and some of these we are applying to, and in a year or two we'll have more results along these lines. So training and testing curves gives very limited insight. They don't take into account hyperparameter fiddling, which is analogous. If you do a lot of hyperparameter fiddling and just report the best results, that's analogous to sort of false discovery claims, right? The training and test curves don't correlate particularly well in our experience with robustness and accuracy or fairness or anything else like that. In a lot of cases, there's no access to data, or you don't have access to the optimization protocols and the hyperparameter fiddling and all this. Can I evaluate systems motivated model adjustments? Can I look at batch size and edge and distillation, but without doing lots of training and retraining? The SVD smoothing, I should have mentioned in a little bit more detail, is interesting because basically you're taking a low rank approximation of the model and you're feeding the original data through it. So if training and testing anti-correlate, you'd expect that to be worse. So this is an example of take the model, modify it by doing a low rank approximation, do no retraining, and then send data through it. So if you have data, you can do that. If you don't have data, you can't. The model user is not the model developer. Sanity check. Did you give me a bad model? Maybe you're an adversary, maybe you're well-intentioned, but you damaged the model. I just want to do a robustness check. And I think if machine learning is really going to become an industrial process beyond a small number of companies that own the whole pipeline, you really have to have these intermediate checks. You want to be able to say, I can't guarantee the model is 100% perfect, but it isn't egregiously bad by metric A or B or C. And so data costs money. Do I have enough data? And this can be the bottleneck for a lot of projects, in terms of generating more data. You either have to buy it or build a system to generate more. Should I put forth that effort, or will I get marginal gain in the model? And so I think all these questions are sort of on the table here, and then we have results on several of them that I'm not going to have time to talk about. But I think these are sort of the questions that a practical theory should be addressing, and I think a lot of the existing approaches don't. Right. So I've been talking about this, these techniques that come from heavy-tailed random matrix theory and statistical mechanics, sort of approaches of learning, very different than was done in the 90s, but still statistical mechanics. And it's very clear that culturally, a lot of people who think about machine learning aren't familiar with this. It's a more scientific approach, and so the question is, can we relate this in a way to something that is more familiar maybe to typical people in machine learning? So let's express this theory in terms of theorems. So there's other versions where we can evaluate things empirically using existing techniques, CKA metrics or connectivity metrics. So Ching Yang, for example, has a nice paper that's going to appear in NERPS later in the year, where he taxonomizes loss surfaces, and he uses very traditional ML metrics to capture ideas like we've been talking about in using tools that are much more familiar to machine learning. So I want to ask that here in terms of theory, but we've done the analogous questions in terms of some empirical results. So data-dependent theory of overparameterization with random matrix theory. So the basic question is, using these sort of statistical mechanics techniques, you can get multiple phases of learning, phase transitions. This was known in the 90s, where you see curves that look like this. In the last few years, it's been popular in machine learning under the name double descent, but it's a corollary basically of some results that people had. I think Opera had results, and some people had results in the 90s where they had essentially these double descent curves. And it basically corresponds to the fact that you get a spike here, and this is like a fluctuational quantity, a volume quantity that diverges at some sort of phase transition. Can you do that? And so the short answer is yes. So this is Zhenhui Liao has some results. I guess this was probably last year at NERPS. We're looking at the difference between entry-wise convergence and norm-wise convergence, can get a very precise characterization of this phase transition as a function of data. So this is, a lot of people have looked at this in recent years, but here this is as a function of the data. And so what you see is that as a function of the data, you get a phase transition here. So this is, and this is a theorem. And so if you're not comfortable with the previous results, what you see is the same sort of thing in an idealized setting here with a theorem. And this uses deterministic equivalence techniques. Exact expression for double descent and implicit regularization the idea is that, so implicit regularization is a term that's been used a lot, but basically now in machine learning, it corresponds to just sort of noise induced by SGD and some related things. But take a step back, the basic question has to do with, I have an approximation algorithm. Theorem, I'm epsilon close to the exact solution, but I'm faster. Theorem prime, I exactly solve exact solution plus lambda times regularization. Can you make that precise? And we made this precise 5 or 10 years ago in different contexts. Here, Michal-Jasinski's made it precise with Feynman-Yang in the context of randomized linear algebra and random sampling just for least squares and ridge and related problems. And so you get the precise expression for this implicit regularization. And what's really going on under the hood on the heavy-tailed approaches is that we're trying to capture the phases of learning, and here we just capture it precisely in the sense of a theorem that may be more familiar with machine learning people in terms of the way they'd like to approach theory. So question, can you take this and extend it to the heavy-tailed approaches we were talking about before? Open problem, but I think it's a great theoretical question. Good classifiers are abundant in the interpolating regimes. So Ryan Thiessen is a student with me, and he's looked at this in terms of evaluating whether the worst case classifiers are typical or not. And the answer is that they're typically not. Uniform convergence approach to learning stresses that essentially worst case, and essentially an overwhelming proportion of interpolating models have very, very small test error, but there's a few worst case things that look bad. And so as the model size grows, test errors sharply concentrate, which is a result having to do with the statistical mechanics approach. Not that you're averaging over something, but that you're averaging over something and the thing you see is typical in this concentration sense. And so here's a theoretical statement to that effect. Open question, can you do that when you have the heterogeneity we saw in the earlier models? And that's something that's a nice theoretical question also to be looking at. How might these processes generate? This is something that Liam Hodgkinson looked at, and there's various mechanisms, and one has to do with analyzing multiplicative weights. There's a lot of work on stochastic gradient descent of the form, the noise at this step is the noise at the previous step, plus some, the weights at this step is the weight at the previous step, plus some additive error. And that additive error sets a scale, and that scale basically gives you a scale analogous to what you have with ridge regression, where you cook in a scale. If you have multiplicative noise, the analysis becomes much, much harder, but you can cook in heavy tail, you can develop heavy tail structure. So this particular theoretical result does it on the weights. Question, can you do it in something like the Fourier domain and on the correlation structure? We don't have that yet, but we're looking at that. But again, a nice theoretical question. This is one way to generate heavy tails. There's other ways. Hessian information at scale. A lot of what people are interested in is looking at gradients and Hessian, very local metrics. We can use related techniques having to do with stochastic optimization. You can actually implement them in pi Hessian or Ada Hessian. And so we have pi Hessian and Ada Hessian that Amir Gholami's and Joyaz really sort of led the charge on, which allows you, it's analogous to Weight Watcher. It's a code base that sits on top of good theory that we and others have developed. And can you now use that to sort of answer questions about loss surfaces, answer questions? And you could do this for training. We've done a lot of that on the right, but you can also use it for validation. And so ask various questions to test hypotheses analogous to what we've been doing. So with that, let me wrap up. Conclusions. I mean, I think the phrase practical theory, some people sort of say, oh, isn't that an oxymoron? And I think if you ask scientific questions, the answer is no, it's not an oxymoron. The point of theory is to make some sort of predictions that guide practice. I think that's not what happens in statistical learning theory oftentimes. It's not what happens that guides the development of machine learning models, but I don't think it's an oxymoron at all. I think practical theory is theory. It uses heavy-tailed, random matrix theory. It uses matrix concentration. It uses expander theory. It uses all these sort of things that are familiar to people that do work on theory and foundations, but it also is theory to do practical things. And so if you need to cheat a little bit, we've cheated on, except for the last 5 or 6 slides, we've cheated on the theoretical niceties in order to make sure that the theory was practically useful for something, such as predicting trends in the quality of state-of-the-art models without access to any training and testing data. the last few slides, we've been going back and revisiting it in a more mathematically precise sense. And I think there's a lot of open questions there raised by our approaches if you're more familiar, if you're more interested in some of the theoretical questions. So I think there's a lot of very foundational questions you can ask here in terms of, for example, are you only looking at additive noise or are you looking at multiplicative noise? Additive is much easier. And so of course, most people do that. Multiplicative is much harder, but it really gets to the heart of what's going on in a lot of these processes. Are you looking at shape parameters or scale parameters? Scale parameters are much easier to work with. Shape parameters are much more realistic in this context. So I think there's a lot of very challenging theoretical questions here, but a practical theory can also be used to ask practical questions. Is my network fully optimized? Should I buy more data? Can I use label or domain knowledge more efficiently? Is my pre-trained model over-parameterized or under-parameterized? Or what does that even mean if you're going to be using it in different ways? So with that, let me wrap up. If you like what we have and want to extend it, pip install Weight Watcher. If you don't like what we have and you want to show it's wrong, pip install Weight Watcher. We've tried to formulate the practical theory in a way that can be reproduced and validated or invalidated. And so I think a practical theory is one that is close enough to practice that it can do that. So with that, let me thank you for your attention. And of course, contact me if you have any questions and we'd be glad to follow up. Thanks a lot.